So we're starting right here, which is just some concentration review. Some of this, hopefully the percent mass and molarity stuff is going to be review. And then you're going to learn some new ways to represent concentration, molality, mole fraction, although you may have gotten that in the gas law unit in Chem 101, depending where you took Chem 101. Yeah, we got some good stuff. We got some good stuff here coming at you. Here we go. So there are two main ways to represent concentration. So concentration tells you how much stuff is dissolved in a solution. And there are two main ways to do that. Mass percent, and I put parts per billion under mass percent. We'll talk about that in a moment. And then molarity. If you are trying to tell the general public that doesn't know anything about chemistry how concentrated a solution is, you're probably going to use mass percent. So for example, if the newspaper is writing an article about how much lead is in the drinking water at a local elementary school, they're going to use mass percent. They're going to use either parts per million or hopefully parts per billion, because hopefully it's not that concentrated, right? Which is a form of mass percent. We chemists, though, when we represent concentration, we 9 out of 10 times want to be in molarity. Molarity is the best way for us. It allows us to do our stoichiometry easily because it's got moles in it, and that is our best way. But you're going to find out tonight that there are other kind of niche concentration units, like molality is going to be one that sounds like molarity, but it's not. So molality is going to be one that we have to use if the temperature's changing. And there's uses for mole fraction and all this stuff. But let's start with the big two, the heavy hitters, mass percent and molarity. So mass percent is this. Mass percent is found, or sometimes called the percent mass of a solution. It's found by taking the mass of the solute, dividing by the mass of the solution, and then multiplying by 100 to make it a percent. Okay, so that's mass percent. So now you really need to know these terms, right? So what is the solute? Well, the solute is the thing that gets dissolved. So if I am going to make a solution, my solute would be this thing that I'm dissolving in there. And then the thing that does the dissolving, that's called the solvent. And together, the solute and the solvent make the solution. So a lot of people like to rewrite this denominator. Instead of saying mass of solution, what they'll write down here is that it is the mass of the solute plus the mass of the solvent. If you really think about it, right, a solution is the thing that's dissolved and the thing that does the dissolving. So the mass of the solution would be whatever the mass of the solute is and the mass of the solvent together. So a lot of people like to rewrite that denominator like that. So, which is what I have right here. So with that said, why don't you try this problem right here? And I'm going to rewrite it on the board while you're trying it. What is the mass percent or percent mass of a saline solution, a sodium chloride solution that contains 25.1 grams of sodium chloride in 220 grams of water? Give it a shot. We'll go over it. You got this. All right, so let's take a look here. The percent mass of a solution is equal to the mass of the solute, which in this case is the sodium chloride, divided by the total mass of the solution times 100. Well, the solution is the solute, sodium chloride, and the solvent, water. So a lot of people like to just put 220 down here, but it's not. That's only the solvent. The percent mass for the solution is going to be 25.1 grams divided by the sum, 25.1 plus 220, and then times 100. Right? So here we go. Sorry, there's still some Windex on the board there, apparently. Let's get that off of there. There we go. All right, 25.1 divided by the quantity, 25.1 plus 220. That's going to be a 10.2% mass solution. So if you make a solution by dissolving 25.1 grams of sodium chloride in 220 grams of water, 10.2% of that solution's mass is coming from the solute, which is sodium chloride. So a couple terms there you got to know like the back of your hand, right? Solute, thing that gets dissolved. Solvent, thing that does the dissolving. And both together, that's the solution. Awesome. Whoops. Parts per million and parts per billion. These are just a special type of percent mass. So when you have very little solute in your solution, then instead of multiplying by 100, because if it's very little, it'd be like 0.0005%, right? If you have very little solute in your solution, then maybe instead of a percent mass, where you only multiply by 100, maybe you want to do parts per million, where really instead of multiplying by 100, you just multiply by a million. And then if you have a really, really, really small amount of solute, then maybe you want to do parts per billion, right? Which is just where instead of multiplying by 100, you just multiply by a billion at the end. Okay, so these problems are actually pretty easy. You just use the percent mass formula and then multiply by a million or by billion. So why don't we give these guys a shot? And here we go. Okay. Let me change this a little bit. So let's do, instead of that, let's do, hang on here, because I have it in micrograms, which is already multiple, it's making it super easy for you. So let's say that lead plus 2 ion concentration is 3.6 times 10 to the negative 6 grams. So let's say the lead plus 2 mass is 3.6 times 10 to the negative 6 grams, right? Which is what micrograms would be. So we're going to pop that in here instead of the 3.6 micrograms. So let's try this top guy together. We got a 5.5 gram sample of well water. It's found to contain 3.6 times 10 to the negative 6 grams of lead ions. What is the concentration of the lead ions in parts per million? So you can see that's a very small amount of solute. So we're going to try, nope, still need Windex, to represent it in parts per million instead of percent mass. Because if we did a percent mass, it would be like 0.0000, right? And this is going to hopefully give us a better way, a nicer looking number to do this. So let me copy this information down here, and then we'll try this guy. So we got the mass of the solution. That's 5.5 grams. We've got the mass of the solute, which are lead ions, and that's 3.6 times 10 to the negative 6 grams, and we want the concentration in parts per million. Awesome. So for this problem, it's going to be the mass of the solute divided by the mass of the solution, and then times a million. So we're going to take the mass of our solute, 3.6 times 10 to the negative 6, divided by the mass of the solution, 5.5. They're both grams, so they're going to cancel out, right? And then we're going to multiply by a million. Now I like to use the E button. So I don't know if you guys are familiar with the E button, but when a number's in scientific notation, I use the EE button, which I'd be happy to show you in lab tomorrow on a graphing calculator at TI-83 at second comma. That's that EE function. So if nobody's ever taught you how to use that EE button, you let me know tomorrow, and we will make it a point to go over it in person. And we can see this is a 0.65 part per million solution. That's a much nicer looking number than if we had used percent mass. It would have been 0.00000000, whatever. The shortcut you can take, and this is what the original problem was. Originally, this was 3.6 micrograms. Well, micro is a millionth of a gram. So if you have it in micrograms, that's like essentially you don't need to multiply by a million then. So you can take a mass in micrograms divided by a mass of the solution in grams, and then you don't have to multiply by a million, or like eliminates that step. Same thing with nanograms. A nanogram is the same as a billionth of a gram. So that's like it's already been multiplied by a billion. So let me show you that with the next one. So if we take a look at this problem, you got 10.5 grams of solution and 6.85 nanograms of mercury. what's the concentration in parts per billion? Well, you can take a shortcut here with this problem. Here's the shortcut we can take. Instead of taking the mass of the mercury and dividing it by the mass of the solution and then multiplying by 1,000,000,000. Since the mass of the solution is in nanograms, okay, well, then that gets rid of this multiply by 1,000,000,000 step because this mass of the solute has already been multiplied by 1,000,000,000 because it's a nanogram. So it's a shortcut you can take. If the mass of the solute's already in nanograms, you don't need to multiply by 1,000,000,000. If the mass of the solute was already in micrograms, then you wouldn't have to multiply by 1,000,000. So we could take a super duper duper awesome shortcut here in this problem. We can take that mass in nanograms, 6.85 nanograms of the solute, mercury, and we can divide that by the mass of the solvent in grams, and that's essentially like it's already multiplied by 1,000,000,000 for you there, right? So 6.85 divided by 10.5, that's going to be a 0.652 part per billion solution, 0.652 parts per billion. Awesome. So that's a shortcut that I wanted to show you. Instead of multiplying by million, you could just measure the mass of the solute in micrograms. And instead of multiplying by 1,000,000,000, you could just measure the mass of the solute in nanograms, like a little shortcut. We won't use mass percent very much in this class. Again, that is kind of for the average Joe, right? But you guys are not the average Joe, at least not for the next 6 weeks. You guys are chemists, and we most often use molarity. So molarity is a formula. We use a capital M to represent molarity, and it is moles of the solute. Sometimes we use an N to represent moles, right? So moles of solute divided by the volume of the solution, and that volume has to be in liters. So right here is the easiest problem you are going to get from me all year. I guarantee it. This is the easiest problem all year. Go ahead and calculate the molarity. If 1.63 moles of silver nitrate is dissolved in a total volume of 4 liters of solution, watch out for sig figs. See if you can get the sig figs right. Go ahead. All right. So this problem should have been pretty darn easy. That's going to be 1.63 moles, and it's going to be divided by 4.00 liters. And that's going to be 3 sig figs divided by 3 sig figs. Those are trailing zeros with a decimal point, so they count. So 1.63 divided by 4.00, and that's going to be 0.408 molar. And then you want to write the identity of it, right? Because it's 0.408 molar what? Well, it's 0.408 molar silver nitrate. Okay, and I can't make that 3 subscripted, but you get the point. So that should be the easiest problem all year. How's this going to get a little more difficult? Well, I'm going to make you do some simple stoichiometry. Instead of me giving you the amount of solute in moles, what if I give you the amount of solute in grams? So, for example, what is the molarity of a solution that has 6.95 grams of sodium phosphate dissolved in 1.5 liters of solution? Give that one a shot. All right, folks, here we go. Just some simple stoich here. So you need to convert this to moles, right? How do we do that? With the molar mass. 6.95 grams of sodium phosphate. We're going to pop that over 1. We got to get that molar mass of sodium phosphate. So here we go. That's 3 times 22.99 plus phosphorus, which is 30.97, plus 4 times 16, which is oxygen. That's a molecular weight of 163.94 grams per mole. So 6.95 divided by that. That's in 3 sig figs. We'll end with 3 sig figs. That's a leading zero. Doesn't count. 0.0424 moles of sodium phosphate. So that's going to be my numerator here. Oh, Leah got booted. So molarity is moles of the solute, that's the sodium phosphate, divided by the volume of the solution, And now we're ready to rock and roll. Y'all just got the numerator. We have the denominator. It's already in liters. So here we go. The molarity 0.0424 moles of sodium phosphate over 1.50 liters. That's going to be 0.0283 molar sodium phosphate. Notice we use a capital M as an abbreviation for molarity. You are welcome to write it as moles per liter. You can absolutely do that, but we're lazy. Like on a bottle, if we were labeling the concentration, we would just put a capital M for molar molarity. And then you should write what it is, right? Because if I just, if I make this solution and I have a bottle, if I just write 0.0283 molar, well, great. 0.0283 molar what? You should tell me what's dissolved in there. Sodium phosphate. Yep. Cool. Uh-oh. So this is a molarity problem of what I call an equal masses problem. So a lot of times you get a problem that's worded like this, and I call these equal masses problems. And when you get an equal masses problem, the first thing you need to do is assume 100 total grams of solution. I'll explain why. So potassium nitrate and water. And sometimes for molarity problems, you'll need the density as well. The density of the solution is 0.985 grams per milliliter. And we want the molarity of this solution. When you see the word equal masses, the first thing you need to do is assume 100 grams of solution. Why? Because now you're going to have numbers to work with. If I assume 100 total grams of solution and it's equal mass solute and solvent, well, it doesn't take a genius. That means that you would have 50 grams of the solute, potassium nitrate, and you would have 50 grams of the solvent, water. And now, if we think about the molarity formula, molarity is the moles of the solute, KNO3, divided by the volume of the solution in liters, we can get the numerator pretty easily. All we need to do is a little of that simple stoich stuff. So why don't you convert the mass of potassium nitrate into moles? Go ahead and get that number. So there's our numerator, folks. We just got our numerator. Our numerator is going to be 0.495 moles of KNO3. So that's our numerator. Now, how do we get the volume? This is the volume of the solution in liters. Well, we have the mass of the solution. The solution, we have 100 grams of solution. That's what we assumed. So this is where we need density, right? How do you go between mass and volume? Density. Density, I had a high school physics teacher. She was atrocious. But the only thing I remember from her, and it stuck with me, and now I teach physics for half of the year sometimes. So anyway, it all worked out, but she was terrible. And a high school physics teacher, she said density was a broken heart. And that stuck with me. If you make a heart and then draw a line through it, density is mass divided by volume, right? M over V. I know. That's pretty good. I guarantee you she didn't come up with that. Anyway, she still left from somewhere. So density is broken heart, mass divided by volume. We have the mass of the solution. We have the density of the solution. We want the volume. So I'm a fan of doing the algebra up front. Density is mass divided by volume. Multiply both sides by volume to get it out of the denominator. Mass equals density times volume. Divide both sides by density. The volume is equal to the mass of a solution divided by the density. So if we take the mass of our solution, 100 grams, and we divide it by the density, 0.985 0.85 grams per mil, we will get the volume of our solution in milliliters. So 100 divided by 0.985, that's a volume, 3 sig figs, of 102 milliliters. But that is a problem. Molarity has got to be moles of solute per volume of solution in liters. That's in milliliters. So now we got to do one more step. How do you go from milliliters to liters? There are 1,000 milliliters in a liter. That's 0.102 liters. So now we can finally plug this in. We got our numerator, 0.495 moles of solute. And now our denominator is 0.102 liters. So 0.495 divided by 0.102, that's a molarity of 4.85 molar potassium nitrate. That's our first equal masses problem of the night. We got some more equal masses problems. We go into an equal masses molality and an equal masses mole fraction problem, I think, tonight here as well. But every equal masses problem, whether you're solving for molarity or molality or mole fraction, the first thing you got to do is assume 100 grams. And then that tells you got 50 grams of solute, 50 grams of solvent, and then you can start working it, right? We take our mass of the solute to moles. We take our total mass of solution to volume of solution using the density problem, and we can get there using the density formula. We can get there.